About one of the simplest statics problems that I could possibly think of to get started with is one that looks like this. Here's a person here which is standing on a wooden plank here, or a plank made out of just about anything, and there's two supports right here. There's a support here and here. So this could be a bridge over a canyon or some play structure in a playground or something like that. But the relevant parameters here are that the board or the plank that the person is standing on has a length L, and the person is standing a distance X from one of the pivots. And so what a question like this typically might ask is something like this. How strong is the force of this support up, and how strong is the force of this support up here? So in other words, if you were going to build two supports to hold maybe a kid in a playground, or perhaps this was actually a bridge instead of a person, it was a bus going across it, just how strong a force would you expect to exist on either one of those pivot points right there? It's a classic torque problem. And so here we go. The way we'll solve all of these, I didn't mean torque problems, I meant statics problems, is we're going to use our famous three torque equations. We're going to say the sum of the x forces has to be equal to 0. We're going to say the sum of the y forces has to be equal to 0. And we're going to say the sum of the torques has to be equal to 0, say around the z-axis, something like that. Those are going to be our three guiding equations for all these problems we're going to work. So the first thing you need to do in a problem like this then is, since you're going to be summing the forces, is to identify all the forces that are acting on this plank here. The plank is our focus here. So we already have the F1 and the F2 labeled. They're pushing up on the plank. We have the weight of the person acting straight down like this. We can call that something like mg. And also, the plank has a weight as well. It is not a massless plank or anything like that. It has its built-in mass as well. And for a uniform plank, the weight of it is always going to act right through the center. So we'll call that capital Mg, something like that. So if we look at the plank, we do see four forces on it. We have F1 and F2. There's two right there. Then we have the weight of the plank itself and the weight of the person. So there's four forces acting on this plank. And just try to remember that in these statics problems, our focus is on the plank right here. We're not too interested in this support or that support. We are analyzing the plank as the object here. And we like to stay at rest. And so what we do then, let's just start proceeding with the statics equations right here to figure out what F1 and F2 are. So although I have the sum of the x forces equal to 0 available to me, I don't need that equation in this problem because there's no horizontal forces. There's no left-right forces in this problem, so we don't need it, but we can use this one here. So the first thing we'll do is we'll say, okay, let's see what happens when we sum all the y forces and set those equal to 0. So if I look at the problem here, I have an F1 up, and I'll say positive, I'll say up is positive. I have the weight of the plank down, and I have the weight of the person down, and I have another push of this side up, like that. And all that's going to be equal to 0. That's the sum of the y forces equal to 0. So we've got the two upwards pushes of the supports, and the weights down. And if I do just a tad bit of algebra on this, just to highlight a little point here, I get that F1 plus F2 is m plus m times g, like that. So if you look very carefully, you already have sort of a preliminary conclusion here, is that if you look at it, the collective upwards push of the two supports has to support the collective downwards weight of whatever happens to be on the plank or bridge, including the bridge itself. So if there was another person or another car or another something on there, I would just keep adding all those masses together and multiply by g, and collectively that's what the two supports would need to sustain in order for the thing to remain in equilibrium. So we're sort of done with that. We don't really have an answer yet because we can't write F1 as equal to something per se. But what we can do now is look at the third equation, which says the sum of the torques are equal to 0. So in order to ever use this equation, the first thing I have to do is I always have to think about where my pivot point's going to be, and that's sort of a free parameter. You can choose your pivot point wherever you want in these problems, but usually we choose a convenient point that makes some unknown variable drop away. So I'm going to put my pivot point right there. Okay. So now what I'm going to do is I'm just going to sort of walk along this plank here, and I'm going to fill in the equation, the sum of the torques are equal to 0. And I'm going to observe a little sign convention for these rotations that looks something like this. I'll say anything that causes a clockwise rotation is positive, and a counterclockwise rotation is going to be negative. I'll sort of use that as my sign convention. Okay, so there we go. Let's just start going down the plank and see if we can identify some forces here. Or excuse me, torques. Okay? So the working equation for torque that we have, you can find out where this comes from in another video here, was Rf times the sine of theta. R is moment arm, F is the force, theta is the angle between the two. So what I'll do then, I'll start looking down the plank. I notice there's this first force right here, right at the moment arm. So if I wanted to add that to my sum right here, say I just want to start filling in this sum, it has a 0 moment arm, even though the force is not 0. And it's the sine of some angle. I don't really know what it is. I don't really know what it is down here because I don't know what the angle is between a force and the axis when they're right on top of each other like that. But it doesn't really matter because there isn't going to be a torque due to F1 because the moment arm is 0. So this whole term here, when we're all done, is going to be 0. And that was one of the reasons for putting the axis of rotation right on this side of the plank, right where F1 is here, because it knocks it out of the torque equation. I'm not going to have the symbol F1 in there. Okay? So you just sort of continue then, sort of going down the plank. And if I sort of proceed and go down this way, the very next force I encounter is the weight of the plank itself. So if I look carefully, here's that moment arm, or the line that connects to the axis of rotation and the contact point of the force, and there's a 90-degree angle in there, so I have the angle between the two. And it looks like if this weight has its way, it would cause a positive or clockwise rotation. So I'll go ahead and add in an L over 2 times big M times G times the sine of 90 degrees. So where did all this come from? Well, this capital MG acts at the midpoint of the rod. That's the L over 2 for a uniform rod. Weight O is actually the center. Then you have the sine of 90 because that's the angle in there. And yes, this will eventually be simplified down to 1, making the problem nice and easy. Okay, so we're sort of going there, okay. Continuing on. If I just sort of continue past the weight, if I continue on, I notice now I have the weight of the person acting at distance x from the pivot. And the person, like the weight of the rod, would cause a clockwise rotation if the person had its way there. So if the person standing here, they would cause the rod to rotate down like that. And that's the positive clockwise motion right there. So the person down here, if I sort of fill in my sum down here, is a distance x from the pivot. Their weight is mg. And then once again, their angle, the angle between the moment arm and the force, is 90 degrees also. So we're getting there, almost done. This will be shown to be 1, of course, in just a minute. But there's one more force. If I keep sort of analyzing past the person, I go, there's the moment arm of the person, here's the moment arm, there's one more force all the way down there, which is the upwards push of the other pivot right there. And you can see if that pivot had its way, it would cause the bridge or plank to rotate up like that, this way. That's a negative direction. So I will have, down here in my net torque equation, I will have a negative L times F2 times the sine of 90 in there as well, and all that's equal to 0. That's the last of my torque equation. So if I bring all these things together and simplify a bit, I will see the L over 2 times the mg plus x times mg minus L times F2 equals to 0. That's what my torque equation gives me. And you can see now we do have a solution for F2 right at hand here. In particular, if I solve for F2, I'll get that it's L over 2 mg plus x mg over L, and you can put a big box around that because you have just found now what the upwards force on this support would have to be to sustain this system to be in equilibrium. This is the contribution due to the weight. This is the contribution due to the person. And notice that it is a function of x here. This F2 is a strong function of x. So yes, it depends on where the person is standing. Where the person is standing will dictate exactly what the magnitude of F2 will be. So there you go. And if you want to know what F1 is, don't forget that you have your equation from the sum of the y forces up here available for use at any time you need it right up here. Now you know what F2 is. You can plug in for F2 right there and solve for F1. And so that would solve the problem for you. You are able now to figure out what F1 and F2 are. And just keep in mind, lastly, as you're done here, that F1 and F2 are functions of x. So it depends on where the person's standing. The upward support forces depends on where the person's standing.